So all a critical number is, here's the definition. It's a number C, which is an x value for us, okay? So C is an x value on the domain of our function. So there's a point on our function, and at that point, it's called a critical number or a critical value of the function if f prime is 0 or if f prime is undefined. So all a critical number is an x value where the derivative is 0 or the derivative is undefined. That is all. So let's take a look at some examples. Let's look at graphical first. Find all critical values of f of x. Well, remember, all we're looking for is where is the derivative, 0 or undefined. So, oh, wrong direction. So we got to find out where the derivative is, 0. Well, since this is f of x, a derivative of 0 means that there's a horizontal tangent line. That can happen in 3 ways. It could happen like this, okay, slope of 0 there. It could happen like this, a slope of 0 there. Or it could happen like this, where it gets flat and then starts going back up again, okay? Well, I guess it could also happen, and I'll draw it here. I'm just writing all over the place here. It could happen in the negative direction as well. There's a horizontal tangent line there, okay? So it could happen 4 ways where the derivative could be 0. And if you're given a graph, that's what you're looking for, one of those 4 ways. So I'm looking here, and it looks like the derivative would be 0 here at this top maximum, but it's discontinuous there anyway. So since the derivative is undefined, where a function is discontinuous, -1 is a critical number. So -1. Okay? Even if this point filled it in here, well, -1 would still be a critical number. Let's just get rid of that point altogether. -1 would still be a critical number because the slope would be 0 there at -1, okay? You all see that? There you go, slope of 0. So -1 is a critical number. And you can see down here this corner. Well, if there's a corner, if the slope changes drastically, if it's not a smooth change, if it changes from one direction to another without going through all the other numbers in between, in this case it's going from a negative direction to a positive direction at one point, that's a corner, then the derivative is undefined there as well. And that's at, get out of here, x, what? At x equals 2. So those are the 2 critical numbers of this function, -1 and 2. Over here on my second function, we have several critical numbers. This is so exciting. Our first critical number is at -3. And you might be saying, well, Mr. Smith, why at -3? Well, because it ends at -3. You can see our function just stops at -3. And since it's not continuous at -3, remember, continuous means it's continuous from both sides. Well, this is not continuous from the left side. So since it's not continuous at -3, the derivative is not defined there. And therefore, since f prime is undefined, -3 is a critical number. Also at -1, there's a corner. So that is a critical number for this graph. At 2, the function is discontinuous. So the derivative is undefined there. So at x equals 2. And at 4, it looks like it is discontinuous. That is true. So it looks like 4 should be a critical number because the derivative is undefined. But remember, let's go back to our definition. The number has to be on the domain of the function, which means that f of x has to be defined at that number. Not f prime. F prime can be undefined, but f of x has to be defined. So when we go back here, f prime was undefined at 2 because there's a corner, but f of x is defined. There's a point there. F of 2 is whatever that y value is. Same thing over here. At -1, f prime is undefined because it's a corner, but the function's defined. It's that y value right there. At 2, it's discontinuous, but it's defined as this value right here. And at 4, it's discontinuous. There's a hole there, but there's no point. F of 4 is never defined, so 4 is not a critical number. If I went ahead and put a point right here, well, now f of 4 is defined, so now x equals 4 is a critical number. So that's a weird little distinction you got to make. The derivative is undefined or 0, but the function has to be defined at that number for it to be a critical number. And that's just a definition. There's no mathematical, real technical reason for that. That's just the definition of a critical number. So that's how you do it graphically. You look for where the derivative is 0, and that can happen in one of 4 ways. 1, 2, 3, 4. And you look for where the derivative is undefined. That happens when the function is discontinuous and when there are corners. And there could also be a vertical tangent. Now, I didn't draw an example of a vertical tangent. I just thought of it, actually. Let's take an example of a vertical tangent. Okay? So let's say our graph was this graph right here. Okay? So right in the center, I can do better than that. There we go. Let's say that's our curve. Well, it's a nice continuous curve. The derivative is defined everywhere except for right here where you can see the tangent line. If you drew a tangent line to that curve, it'd be vertical. Check it out. It'd be a vertical tangent line. And since a vertical line has an undefined slope, the derivative is undefined at that point. So this value right there, I'm just making that up, if it was -2, x equals -2 would be a critical number of this function because the slope is undefined there. All right. So that's how you do graphically. If you're given a function and you're asked to find the critical numbers, all you need to do is find out, so same thing, where's f prime 0, where is it undefined? Well, that's easy. Is that right? Yeah, f prime of c is undefined. Yeah, there we go. We got to find the derivative and find out where it's 0 and undefined. So for number 1, f prime of x, this is no big deal for us master calculus people. It's just 2x minus 3. Well, 2x minus 3 is a linear function. It's never undefined, but it is 0. It's 0 at 3/2, okay? Now, I'm not saying f prime has to equal 0. That's not what's happening here. I'm setting it equal to 0 to find out what x value makes it 0, because that x value will be a critical number. So this x equals 3/2 is a critical number because f prime of 3/2, this is why, f prime of 3/2 is 0. That's why 3/2 is a critical number. All right. Come on now. I hate when I do that. Get out of here. So, number 2. F of x is a cubic function. All right, no problem. It should make sense also that a parabola, x squared, is a parabola. Remember that. Well, that should have one critical number. This is a parabola opening upward, so whatever it looks like, it has to look like this. And its critical number has to be where the slope is 0. Well, that's down here. Okay? So right now we know about this function that its vertex, its minimum value, was at x equals -3/2. And that's because we found the critical number, and since the parabola only has one critical number where the derivative is 0, it must be at that value, which was 3/2. Okie dokie. You might also, if you remember this formula from back in Algebra 2, the vertex of a parabola is -b over 2a. Well, check this out. Watch this magic. -b is -3. Well, that's +3. A is 1, so 2a is 2. And you find out that the vertex is at 3/2. So really, when you learn this rule right here, although you didn't know it, you were doing some calculus. Or using a result from calculus, I guess. Okay, moving on. F of x equals x cubed. Well, a cubic could have 2 critical values. Okay, a cubic looks like this. It could have a critical value here and here. It could have one critical value. It could look like that. Then it has a critical value right there where it's horizontal. Or it could have no critical values. A cubic could look like this, where the slope is never 0 and it's never undefined. So for this one, we have possibilities. We're going to check it out. All you do is you find f prime of x and you find out where it's 0 or undefined. So f prime of x is 3x squared minus 8x plus 5. And I'm hoping that factors. We want to find out where is this thing 0. Remember, when you have a quadratic and you want to know where it equals 0, you got to factor it. So you're going to factor this, and if it did factor, we could just do the quadratic formula. But I'm pretty sure this factors, right? 15, what's that, -3, -5, yeah. So this should factor. So we should be able to do, I think, oh yeah, -5 and x minus 1. You're thinking, you're a calculus teacher, you should be able to factor. It's been a long day, give me a break, right? This is how this thing factors. So the zeros of our derivative are x equals 5/3 and x equals 1. These are the critical numbers, okay? Now, again, I'm not setting this equal to 0 just for fun, arbitrarily. I'm not saying it has to be 0 everywhere. I'm saying where it is 0 is where the critical values will be. And it is 0 at these numbers, so these are, I call them crit values or crit numbers. These are crit numbers. There you go. Oh, man, what is happening? There we go. X equals 5/3 and x equals 1. That's for number 2. And really what this tells us now is this cubic function, this cubic graph, has to have a slope of 0 at these points, right? At 1 and at 5/3. Well, we know that a cubic function, if it has 2 critical values, looks like this. As long as the leading coefficient's positive, that's what a cubic function looks like. Well, here's my first critical value. Here's my second critical value. Well, guess what? This happens when x is 1, and this happens when x is 5/3, because 5/3 is bigger than 1. So this really tells us a lot about this function. And we're going to use that knowledge later on to actually start graphing functions with calculus. We're going to be human graphing machines. All right. Number 3, h of x equals 1 over x squared. All right. H prime of x, using the fact that 1 over x squared is the same thing as x to the negative 2. H prime of x is negative 2x to the negative 3. Right? Power rule. Negative 2 comes down. X, subtract 1 off the exponent to the negative 3. So this is negative 2 over x cubed. What's happening here? Come on, computer. Cubed. There we go. All right. So negative 2 over x cubed. It turns out that this thing never ever equals 0. Remember, for a fraction to equal 0, the numerator has to be 0. Well, this numerator never equals 0. So no big deal. Derivative never equals 0. But we also have to check and see where is it undefined. And negative 2 over x cubed is undefined. So h, I got to write this slow, prime of x is undefined at x equals 0. So 0 could be a critical number because the derivative is undefined there. Remember, the derivative has to be undefined, and the x value has to be on my function. The function has to be defined there. So we got to check, is my function defined at 0? And we come back over here to h of x. H of 0 is 1 over 0, which is not defined. So this has no critical values. All right, last one. Now we got this e to the x squared. You're thinking, oh, crap. Why? Why exponential functions? Well, I'm going to show you that it's really not that bad. So we do the same thing. If you want to find the critical numbers, just derive this bad-looking thing. And we got to do the product rule, okay? We have x and e to the x squared being multiplied. So we derive it first. The derivative of x is 1 times e to the x squared. So that's just e to the x squared plus, leave the first, that's x, and multiply by the derivative of e to the x squared. Well, an e to anything when you derive it stays the same. So there that is, e to the x squared. Then we have to multiply that by the derivative of what's inside. We use our chain rule, and the derivative of the exponent is 2x. So we have to multiply by that. There we are. So we simplify. X and 2x, that makes 2x squared. And we're still multiplying by e to the x squared. So that's what g prime of x equals. This thing is never undefined, so that's not a worry here. But we've looked for critical numbers. I want to know, where is this thing equal to 0? Well, I'm going to let you in on a secret. If you look at this, you're like, oh my god, I have no idea how to solve this. Well, all you need to do, my friend, is factor it. If you have a bunch of e to the x and they're all the same thing in each term, you can factor out that e to the x squared. Okay, so we can look at this. All we have is two terms. We have e to the x squared and we have 2x squared e to the x squared. Well, we can factor out e to the x squared from both of those. And that's going to become e to the x squared times 1 plus 2x squared. Now, since we're multiplying two things here, we're multiplying this times this, the only way to get a product of 0 is if one of these two things is 0. So really, you would split this up now. E to the x squared equals 0, and, or I guess, 1 plus 2x squared is 0. Well, e to the x squared equals 0. Maybe you're thinking, oh, God, that's tough. I don't know. But e is just some number. It's a little bigger than, a little bit less than 3. And if you raise 3 to any power, regardless of if the power is positive or negative, 3 to any number is always a positive number. So this has no solution. Okay? So e to any number is always a positive number. So e to the x squared, always positive, means it can't not be 0. This has no solution. Over here, 1 plus 2x squared, you can try and solve this if you like, but I know, thanks to my power, my mathematics here, 1 plus 2x squared is a parabola, and it's raised up 1, and it's stretched vertically by 2, so it really, the graph looks like this. And I know that this graph here, this is 1 plus 2x squared, never, ever, ever hits 0. It's always positive. So also has no solution. And this, what I graphed over here, this is not a graph of my function x e to the x squared. This is a graph of 1 plus 2x squared. Okay, so I do not mean to confuse you by graphing that there. So this has no solution as well. If you try to solve this, you're going to get imaginary roots. So no solution. So since the derivative never equals 0, it's never undefined, it has no crit numbers.